Here's how rearranging these four congruent right triangles proves the Pythagorean theorem. Take a look at the negative space. It has an area of c squared. Now let's push those triangles to the sides so that there are two squares of negative space, with an area of a squared and b squared. The area of the negative space must still be the same because the triangles haven't changed in area. So we get one visual proof of the famous Pythagorean theorem. There are a lot more, so let's take a look at them. The Pythagorean theorem, or at least some variation of it, has been around for literally thousands of years. When the sides of a right triangle are all integers, those integers are called Pythagorean triples. The ancient Babylonians and Egyptians calculated Pythagorean triples between 2000 and 1800 BCE. The Baudhayana Satra Sutram, a Hindu text from at least 500 BCE, gave an equivalent statement of the theorem. The diagonal of a rectangle produces both areas which its length and breadth produce separately. Pythagoras and Plato also computed Pythagorean triples, and Euclid provided proofs in Elements, one of the first books on classical geometry. A proof is given in the Chinese book Zhou Bi Suan Jian. Polymaths Tabit ibn Qurra and Leonardo da Vinci both produced original proofs. More recently, James Garfield also created his own proof in 1876 before becoming a United States president. With so many proofs, Elisha Scott Loomis, an American mathematician, undertook the monumental task of compiling all the proofs known to him. His book, The Pythagorean Proposition, was published in 1927 and showed 367 different proofs. It correctly stated that there are actually infinite numbers of algebraic and geometric proofs. However, he also asserted that trigonometric proofs are impossible because the trigonometric identity cosine squared x plus sine squared x equals 1 relies on the Pythagorean theorem, making any argument circular. In 2009, Jason Zimba showed Loomis's assertion to be wrong by using two subtraction formulas to derive the Pythagorean identity. Zimba is a mathematician and educator in the United States that has contributed to its National Common Core standards for K-12 educational achievement. So interestingly, the next two figures in this history are K-12 students in the United States, or at least they were when they used trigonometry to formulate their own unique proofs of the Pythagorean theorem. Calcea Johnson and Nikia Jackson, two black girls from New Orleans, Louisiana, were high school seniors when they created these proofs and presented them at a mathematics research meeting. At the time, the students and their teachers didn't know about Jason Zimba's 2009 proof and presented their proof as an impossible proof of Pythagoras because of Loomis's claim. Whether because of their astonishing achievement, age, gender, race, or background, Jackson and Johnson received both immediate acclaim and criticism. However impartial mathematics itself might be, its representation is always filtered through people. So let me give you my filtering of their proof. Let's start out by remembering that 1 plus p squared plus all the infinite powers of p equals 1 over 1 minus p if p is between 0 and 1. This is called a geometric series. By definition, the series equals the sum of all the different powers of p, starting at I equals 0, which is 1. We know that p times that sum equals p plus p squared plus p cubed plus all the other powers of p. And then if we subtract equation 2 from equation 1, we get 1 minus p times that series equals 1. Think about the series symbol like any variable. X minus x times p equals x times 1 minus p by factoring out the x, except x is the infinite sum of all the different powers of p. Then all we have to do is divide both sides by 1 minus p to find the value of the infinite series. We've successfully derived the value of a geometric series, so let's use it to prove that xy equals zy over 1 minus p if xz is p times the length of xy and z lies on xy. In other words, they have a scaling factor of p, where p is between 0 and 1. It can't be greater because then it'd be longer than xy. It's pretty clear that the length of xy is the sum of zy and xc. Remember that xc is p times the length of xy, so we get xy equals zy plus p times xy. xy is still zy plus xc, so let's make another replacement. Similarly, xc is still p times xy, so we can make yet another replacement. And then we can make another, and then another, and another, and another. Hopefully at this point it's clear that this pattern will continue on forever and that it'll give us xy equals zy plus p times zy plus p squared times zy plus p cubed times zy plus all the powers of p times zy, or xy equals zy times all the powers of p. By our previous mini-proof, we have that xy equals zy times 1 over 1 minus p.
Now we're finally ready to see some right triangles. Let's start out with our archetypal triangle ABC with side lengths little a, b, and c. For now, let's say that neither angle A nor angle B equals 45 degrees.
Using the information from triangle ABC, let's make another triangle x, y0, y1 to help us out. This triangle has some special properties. Angle y0 has the same measure as angle A, and angle y1 is 90 degrees plus the measure of angle A. It now makes sense why angle A and B can't equal 45. If they did, these two sides would be parallel, and there would be no triangle. Now let's draw a line down from y1 so that we have a right angle on this side. Now the other side is equal to angle A. Draw a line from the new point z0 to the side so that it makes another right triangle. From the midpoint of the y0, y1 line, draw a line that's perpendicular to it. We'll extend our x1's line so that it meets this new line at x prime. Then connect x prime with y0.
Then all of the right triangles that we've made are just different scaled versions of our initial triangle because they all have the same angles, aka they're similar triangles. This upper right triangle has the same angles because the same line is intersecting two parallel lines, and this upper left triangle is actually congruent to it because this line is a perpendicular bisector. If you remember from high school geometry, the angle-angle similarity theorem gives us that triangles with the same angles are similar. Let's label all of our similar triangles with side lengths. Knowing that they're similar or scaled gives us a lot of relational information about them.
For example, we can compare j over h to a over b and h over f, short leg over long leg, with this representation. Multiplying j over h by h over f cancels the h and gives us a over b squared on the right-hand side. We noticed earlier that we got all those similar right triangles, but we actually have another pair of similar triangles, x z0 z1 and x y0 y1. Since j and f correspond to each other on these two triangles, their ratio is the scaling factor between the two triangles. That means that the ratio between x y0 and x z0 is the same, as well as the ratio between x y1 and x z1. This helps us to finally apply that line segment statement that we proved earlier. That statement applies to pairs of line segments with a scaling factor of p, and we just got two such pairs of line segments. In that earlier proof, we split up a line segment into two parts and found that the segment equaled the first part divided by 1 minus the other part's scaling factor with the segment. For our current line segments, x y0 and x y1 are the segments. We know the ratio of x y0 to x z0, so let's use it. We also know that x z0's length is g. Since this triangle is similar to our original triangle, g over f equals c over b, and g equals f times c over b. Plugging that in gives us x y0's length, almost completely in relation to the original triangle's side lengths. We can do the same for x y1.
You might be wondering, that's cool, but we haven't used the top part of our construction at all. We also haven't used trigonometry yet. When we're making a proof, we usually don't make something without using it, and I did say that this is a trigonometric proof.
Notice that this angle is b, so this one must be as well. The angles on a triangle add up to 180, and the last angle is 90, so angles a plus b must also be a right triangle. So this is a right triangle that we can do some trigonometry on. Sine 2a equals opposite over hypotenuse, or x y0 over x prime. X prime is x y1 plus this d length segment. D divided by half of this segment is equal to c over a, so d equals f over 2 times c over a. Plugging that in eventually gives us a formula for x prime that only involves f and the original triangle lengths. That's very helpful because when we plug it in, the f's cancel each other out, giving us a definition of sine 2a that only involves the side lengths of the original triangle. We can use sine in a different way with the law of sines. The ratio of sine of 2a over f should equal sine b over d. We just calculated d, and we already know that sine of b is b over c. That gives us that sine of 2a is 2ab over c squared.
So we know that sine of 2a equals 2ab over a squared plus b squared. and also 2ab over c squared. That proves that a squared plus b squared must equal c squared for all non-isosceles right triangles. When angle A and angle B both equal 45 degrees, looking at it this way gives us a proof for this special case. And so we've arrived at the end of Jackson and Johnson's proof of the Pythagorean theorem.